In the previous videos, we looked at the definition of the limit, how it's related to the standard part, as well as computing left-handed and right-hand limits, again, using standard parts. So here I want to make clear the relationship between standard parts and limits. So remember our rules for standard parts. For instance, if I've got a real number, k, then it can slide right out or factor out of the standard part. And so the standard part of KB would be k times the standard part of b, provided k is real. Same thing goes for limits, that if I've got a constant times my function, I can factor it out. And so k is just times that limit. Similarly, the standard part distributes across addition and subtraction, so does the limit. So if we got the limit of the sum or difference of two functions, that's the same as the sum or difference of those two limits. And same is true for products. Standard part of a times b is the standard part of a times standard part of b. And similarly, if I've got the limit of the product of two functions, that's the product of their limits. And if I've got ratios, I've got the standard part of a over b, that would be the standard part of a divided by standard part of b, of course, provided the standard part of b isn't 0. Same is true for my limit. If I look at the ratio of f of x over g of x, the limit as x approaches c, this is the ratio of their limits, provided that this limit isn't 0. And standard part can pass through into the radical, provided that this is, if n is even, really the key is that this thing has got to be positive. Same goes here, that the limit can slide right into the radical, again, provided this radical is defined. And really, the issue here is n even? If n is odd, then cube root, fifth roots, all those, they're defined for all positive and negative values. But if this is an even number, so the square root, the fourth root, the sixth root, then it only makes sense if this in here is positive. Let's take a look at a couple of examples of computing limits in which I just use those limit rules instead of actually going to the standard part. Let's compute the limit as t approaches 0 of t cubed minus 2t squared plus 4, all divided by 3t squared minus 5t plus 7. So in all of the previous examples, we would have computed we would have said, okay, let's let h be infinitely close to 0, since that's the limit, and compute standard parts. But again, I want to use the rules here. So we know that 1, provided that the limit of the limit of the denominator isn't 0, that the limit of the ratio is the ratio of the limits. This is equal to, oops, I don't know why I'm in red now. This is equal to the limit as t goes to 0 of t cubed minus 2t squared plus 4 divided by, oops, the whole thing, divided by the limit as t goes to 0 of 3t squared minus 5t plus 7. And now the limit distributes across addition and subtraction, and for the for the sake of your time, I'm not going to rewrite this out and break it up into 6 different limits, but just kind of ask ourselves a question. Well, as t gets infinitely close to 0, so it's going to be, this function right here, t cubed, is going to get close, is going to, in the limit, go to 0, right? And this, as t gets infinitely close to 0, this is going to get close to 0. And then 4, well, there's no t in it, so it would just keep at 4. And here, 3t squared, it's going to 0. 5t, it's going to 0. And 7 is going to 7. Putting that all together, we see that the limit of the top is 0 minus 0 plus 4, so that's equal to 4. And the limit on the bottom is 0 minus 0 plus 7, so the answer is 4/7. And we're done. That is the limit. In fact, I could have just done it here. Looked at this, said, oh, 0, 0, 4, 0, 0, 7. Okay, excuse me. Let's look at another example. So the limit as x goes to 3 of x cubed minus 3x squared minus 4x plus 12, all divided by x squared minus 4x plus 3. Now let's kind of do the same thing we talked about at the top. So we're going to let x, now it's not going to 0, it's going to 3. So this is going to be going to 3 cubed, which is 27. This is going to go to 3 squared times 3, which is going to 27. This is going to 4 times 3, which is 12. And this, of course, is going to 12. The bottom is going to 3 squared, so that's 9. This is going to 4 times 3, which is 12. And this is going to 3. So, putting that together, we get that the top is 27. So there's a minus, 27, a minus, and a plus. This will be a minus and a plus. So the top is 27 minus 12 and 7, that's 0, minus 12 plus 12, so that's 0. And the bottom is 9 minus 12, which is minus 3, plus 3, which is 0. Oops, that's a problem. But if I were to be taking standard parts, I would know that the top is infinitely close to 0, bottom is infinitely close to 0, so these guys are infinitesimals. This is an indeterminate form, so I don't stop. Right? This is, I've got to stress this, don't stop. Don't now say it doesn't exist. You've got to do some algebra. Okay, so this is not true. It's not equal to 0 over 0, but I can do a little bit of algebra here. So this is equal to the limit as x approaches 3. And let's see how the top factors. Well, I've got a cubic here, but I see that I've got an x squared and x cubed here, and I've got a 4 and a 12, so there's some hopeful things to cancel. So the top, I can factor, the first two terms, I'll factor an x squared out. So I get x squared, and what gets left is x minus 3. And here I'll factor a 4 out, and I'm going to keep the sign to it, so this will be minus 4. And it's x, and then that gives a minus 3 left behind. So that's how the top's going to factor. The bottom factors into, let's see, it's a 3, so there's a 3 and 1. It's got to add up to 4, so the bottom will be x minus 3 times x minus 1. And now that's a good sign, because check it out. I've got a common term of x minus 3 on both sides here, and an x minus 3 on the bottom, so they cancel, which is what I'm always looking for when I've got indeterminate form. I've got indeterminate form, I want to look for canceling. And I got it. So this is the limit as x approaches 3 of x squared minus 4. And on the bottom, I have x minus 1. So let's try it again. If x approaches 3, this is approaching 9. And 4 is staying at 4. X is approaching 3. And 1 is staying at 1. So the top looks like 9 minus 4. The bottom looks like 3 minus 1. So this is 5 halves. And there's our answer. The limit is equal to 5 halves. So we can use the fact that standard part rules are intimately related to limit rules and use those limit rules instead of going to the standard parts and kind of saying, okay, let's say h be infinitely close to 3 and look at the standard parts and work it all out. Instead, we can use the fact that the limits distribute across multiplication, distribute across addition, subtraction, division, square roots. In fact, it'll distribute across any what we call continuous functions. But that's the next chapter or next section, and so we'll talk about that then.